Welcome. Friends, I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the cold reaches between stars, where objects drift for millions of years, carrying stories written in ice and stone from suns that aren't ours. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The telescope array in Hawaii captures photons that have traveled across distances the human mind smooths into numbers but cannot truly hold. Each pixel of the detector records light that left its source when the object was already in motion, already committed to a trajectory that began before any human eye turned skyward. The software flags an anomaly, not dramatic, not bright, just present in a way that doesn't match the expected catalog of solar system residents. An orbit that's wrong, too steep, too fast. The eccentricity value sits beyond 1.0, which means this thing isn't circling back, it's passing through. The astronomer reviewing the data feels a small tightness in her chest, the kind that comes not from certainty, but from the arithmetic insisting something impossible is simply true. She runs the calculations again. The hyperbolic trajectory holds. The velocity vector points to an origin outside the sun's gravitational dominion, outside the Oort cloud, outside the 50,000 astronomical unit bubble where comets sleep and wait. This object came from somewhere else. Only took 4.5 billion years for humans to notice the first one. And now here's another candidate, appearing in the data like a quiet stranger at the edge of a campfire's light. The designation is provisional, a string of letters and numbers that will change as more observatories confirm what Hawaii suspects. For now, it lives in an email subject line, a Slack channel, a hurried phone call to colleagues in Chile where the darkness is just beginning and the telescopes are waking. The object itself knows nothing of this attention. It continues moving, as it has moved for an unimaginable span, through regions of space where the temperature hovers a few degrees above absolute zero and the density of matter is measured in atoms per cubic meter. It is profoundly alone. It has been alone for longer than complex life has existed on Earth. The irony, of course, is that interstellar space is not empty but merely patient. Hydrogen atoms drift. Cosmic rays thread through the dark. Magnetic fields twist in configurations no instrument has mapped. The object passes through all of this at 12 kilometers per second relative to the local standard of rest, which is itself moving, which is itself embedded in a galaxy rotating at 220 kilometers per second around a center 26,000 light-years away. Everything is in motion. Nothing holds still. And yet, from the object's perspective, if objects could hold perspectives, the stars barely shift. The constellations remain fixed, because even at these speeds, the distances are so vast that change unfolds on timescales measured in millennia. It carries ice. Probably. Most objects born in the cold outer regions of stellar systems carry water ice, carbon dioxide ice, methane frozen into lattices that haven't seen warmth since the protoplanetary disk cooled and collapsed. But this ice formed around a different star, condensed from a different nebula, incorporates isotopic ratios that might deviate slightly from the solar system's well-measured norms. The ice remembers, not consciously, but chemically. It holds within its crystalline structure the temperature and pressure and radiation environment of its birthplace, a star system humans will never identify because the object's trajectory cannot be traced backward with enough precision to pinpoint an origin. The angles are too uncertain. The gravitational perturbations from every star it passed too cumulative. The models that predict how such an object should behave are built from solar system data. 4.6 billion years of local history. Thousands of comets observed, catalogued, measured as they swing around the sun and boil away their volatile ices in spectacular tails that stretch for millions of kilometers. The physics is well understood: sublimation rates, gas production, dust ejection. The brightening curve as an object approaches perihelion, the fading as it retreats. These models work. They work so well that when a new comet is discovered, astronomers can predict its brightness months in advance, can estimate its size from its magnitude, can infer its composition from spectroscopic lines. But this object, this provisional designation hanging in the data, doesn't seem interested in cooperating. The preliminary brightness measurements come in fainter than expected. The spectroscopic observations show absorption features that don't quite match the templates. The outgassing, if it's happening at all, is so subdued that the instruments struggle to detect it. A comet from another star should still be a comet. The laws of thermodynamics don't change between star systems. Ice should sublimate when warmed, gas should escape, a coma should form. And yet, the data whispers something else, something quieter, something the models didn't anticipate. The astronomers begin writing observing proposals, time on larger telescopes, spectroscopic follow-up, photometric monitoring. The object is still months away from its closest approach to the Sun, which means there's time. But not much. Interstellar visitors move fast. They don't linger. They don't return. This will be a single pass, a brief intersection of trajectories, and then the object will climb back out of the Sun's gravity well and resume its journey through the galaxy. In a few thousand years, it will be light years away. In a few million years, it will pass near other stars, other planetary systems, other worlds that may or may not be watching. The mystery is not that the object exists. The galaxy contains hundreds of billions of stars, each potentially surrounded by the debris of planet formation, and gravitational interactions between planets and planetesimals can easily eject small bodies into interstellar space. The galaxy should be full of such wanderers. The mystery is that humans are only now beginning to detect them, only now building telescopes sensitive enough and sky surveys comprehensive enough to catch these faint, fast-moving visitors against the background of distant stars. The first confirmed interstellar object was detected in 2017, only 8 years ago, which means the entire human understanding of what interstellar objects look like, how they behave, what they're made of, is based on a sample size that can be counted on one hand. This one, this quiet anomaly, adds another data point. But data points are supposed to clarify. They're supposed to sharpen the picture, refine the models, bring the universe into focus. Instead, this object seems to blur the edges, to introduce new questions without answering the old ones. It sits in the telescope images like a challenge, like a reminder that the universe is under no obligation to make sense on human timescales or within human frameworks. It simply is. It moves. It reflects a tiny fraction of the sunlight that reaches it, and that fraction is enough to register on silicon detectors orbiting Earth, and that registration is enough to trouble the models, and the trouble is enough to keep astronomers awake at night, staring at data that refuses to resolve into clarity. The object doesn't care. It continues its trajectory, indifferent to observation, indifferent to theory. It has been moving through the dark for so long that the Sun is just another star it happens to be passing, briefly, before resuming the endless drift between stellar systems. Only took billions of years to get here, and it won't stay. The term interstellar carries weight that the syllables don't quite convey. 4 beats, casual in conversation, but the meaning stretches across distances that collapse language into inadequacy. Between stars. the space that separates one stellar system from another, the gulf where gravity weakens to whisper and light from the nearest sun takes years to arrive. Arriving not as warmth, but as faint radiation, barely distinguishable from the cosmic microwave background, an object moving through this region moves through a darkness so complete that human eyes, evolved to detect photons in a narrow electromagnetic band, would register nothing. Not black, not shadow, simply the absence of signal. The physics of interstellar travel, even for an unconscious lump of ice and rock, requires speeds that dwarf human experience. The object currently approaching the inner solar system moves at roughly 26 kilometers per second relative to the Sun, fast enough to cross the diameter of Earth in 8 minutes, fast enough that atmospheric entry would vaporize it instantly if it somehow found itself on a collision course with a planet. But in interstellar terms, this is not fast, this is glacial. At this speed, reaching the nearest star system, Proxima Centauri, 4.2 light-years distant, would take 70,000 years, and the object hasn't been traveling in a straight line toward any particular destination. It's been drifting, nudged by the gravitational fields of stars it passed millennia ago. Its trajectory, a cumulative result of perturbations that cannot be untangled. The radiation environment between stars is quieter than the bombardment near a sun, but not silent. Cosmic rays thread through the dark, high-energy particles accelerated by supernova shockwaves and magnetic field interactions, striking any object in their path and slowly altering its surface chemistry. Over millions of years, this radiation processing darkens ices, breaks molecular bonds, creates complex organic compounds that wouldn't form in the sheltered regions near a star. The surface of an interstellar object becomes a record of its exposure, a chemical diary written in carbon chains and radiation damage. The deeper layers remain pristine, frozen in the state they held when the object was ejected from its birth system. But the outer few centimeters or meters, depending on size, are transformed into something else. Something that has no analog in the solar system's protected comets. The first humans to consider interstellar objects seriously were not astronomers, but science fiction writers, who understood intuitively that a galaxy full of stars must produce wanderers. The math came later. In the 1970s and 1980s, astrophysicists calculated ejection rates from planetary systems, estimated the density of interstellar objects drifting through the galaxy, and concluded that at any given moment, several such objects should be passing through the solar system's neighborhood, but detecting them required telescopes that didn't exist yet, survey programs that hadn't been funded, algorithms that hadn't been written. The objects were out there, moving through the dark, unobserved and unobservable, until technology caught up to theory. The irony is that once the technology arrived, the first detected interstellar object turned out to be deeply strange. Oumuamua, discovered in 2017 by the Pan-STARRS telescope in Hawaii, behaved like nothing in the catalog. It showed no cometary activity, no coma, no tail, no detectable outgassing. Its light curve suggested an elongated shape, tumbling end over end, with a brightness variation that implied either a cigar-like geometry or a pancake flat disk. It accelerated slightly as it moved away from the sun, a non-gravitational force that comets exhibit when outgassing pushes them off course. But no gas was detected. Astronomers proposed explanations ranging from mundane, maybe it was outgassing something invisible, maybe the instruments weren't sensitive enough, to exotic, involving everything from hydrogen icebergs to alien spacecraft. The object didn't wait for consensus, it left the solar system and faded beyond detection, carrying its mysteries back into the dark. The second interstellar object, 2I/Borisov, arrived in 2019 and was blessedly normal. It outgassed, it developed a coma. Its spectrum showed familiar signatures of water vapor and carbon monoxide. Its nucleus brightened as expected when approaching the sun and dimmed as it retreated. Scientists studied it intensely, relieved to find that at least one interstellar visitor behaved like a comet should. The models held. The universe made sense again. The strange case of Oumuamua could be filed away as an outlier, a statistical anomaly, the kind of weird edge case that every dataset contains if you look long enough. But now, here is this third candidate, this provisional designation, and the early data suggests it might not fit the pattern either. The brightness is wrong. The spectrum is ambiguous. The outgassing, if it exists, is so faint that observers aren't sure whether they're detecting real signal or instrumental noise. It's too early to draw conclusions. The astronomers caution, more data is needed, better observations, higher signal-to-noise ratios. But the unease is already present. The quiet suspicion that the sample size of interstellar objects remains too small to establish what normal even means. The object itself remembers nothing of its origin. It has no memory, no awareness, no record of the star it once orbited or the planetary system that ejected it. The ejection likely happened during the chaotic early phase of that system's formation, when gas giants migrated inward or outward, scattering smaller bodies into eccentric orbits that eventually intersected with other planets, producing gravitational slingshots that flung some objects into interstellar space. This is a common process. Simulations show that every planetary system should eject billions of small bodies during its formation. The galaxy is full of orphans. What's unusual is the chemistry those orphans carry. Each star forms from a molecular cloud with a slightly different composition, the ratio of oxygen isotopes, the abundance of deuterium, the concentration of carbon versus nitrogen. These vary depending on the cloud's history, its proximity to previous supernovae, its temperature and density during collapse. An object formed around one star will carry isotopic fingerprints distinct from objects formed around another. In principle, spectroscopic analysis of an interstellar visitor could reveal not just that it came from elsewhere, but something about the chemical environment of its birthplace. In practice, the objects are too faint, the exposure times too short, the spectral lines too blended to extract such fine details. The instruments are almost good enough, but not quite. The distance between stars is sometimes described as vast, but vast is a word that flattens the reality. The Sun's nearest neighbor, Proxima Centauri, is 40 trillion kilometers away. If the Sun were a grapefruit in New York City, Proxima would be another grapefruit in Los Angeles, and the space between would contain, on average, about one hydrogen atom per cubic centimeter, not empty, but close. An object crossing this space encounters almost nothing. No drag, no friction, no interaction except the faint pressure of starlight and the occasional impact of a cosmic ray. It coasts. For millions of years, it coasts, its velocity unchanged except for the subtle gravitational tugs of distant stars. This object has been coasting for an unknown span. Its ejection from its birth system could have happened 1 million years ago or 100 million, without knowing where it came from. There's no way to calculate how long it's been traveling. It could have passed through regions of the galaxy rich in star formation, where young massive stars flood space with ultraviolet radiation. It could have drifted through the galactic halo, where the density of stars drops and the isolation deepens. It could have been grazed by the shockwave from a nearby supernova, though the odds of such an encounter are vanishingly small. All of this remains speculation. The object carries its history silently. The models predict that interstellar objects should arrive from random directions, distributed evenly across the sky, because the galaxy's rotation mixes trajectories over time. But the sample size is too small to confirm this. 3 objects, possibly 3, if this one's interstellar nature is confirmed, don't constitute a statistical population. They're anecdotes, interesting anecdotes, certainly, but not enough to build a theory of interstellar object demographics. Astronomers need dozens of detections, hundreds ideally, before patterns emerge. And so the surveys continue. Telescopes scanning the sky night after night, algorithms flagging anything that moves too fast or in the wrong direction, hoping to catch the next visitor before it vanishes. Only took 4.5 billion years for the first one to be noticed. And now, the waiting continues. Patient and unending, for the data to accumulate. The first one arrived without warning, which is to say it arrived exactly as physics dictated, but human observation lagged behind. Oumuamua, a Hawaiian word meaning scout or messenger sent ahead, was discovered on October 19, 2017, already past its closest approach to the Sun and heading outward. The Pan-STARRS telescope captured it as a faint streak against the background stars. Moving at 87 kilometers per second relative to the Sun, far too fast to be gravitationally bound. By the time astronomers calculated its trajectory and realized what they were seeing, the object was already leaving, already fading, already beyond the orbit of Mars and accelerating into the outer solar system. The shape remained uncertain, but the light curve told a story. As Oumuamua tumbled through space, its brightness varied by a factor of 10 over a period of roughly 8 hours, suggesting an elongated form with an axis ratio of at least 6:1, possibly 10:1. Imagine a cosmic cigar, or perhaps a needle, spinning slowly as it moves. No solar system asteroid or comet exhibited such extreme elongation. The closest analogues were certain binary asteroids where tidal forces had stretched the material, but those were gravitationally bound pairs, not single objects. Oumuamua appeared to be a monolith, a single coherent piece, tumbling end over end for reasons unknown. The spectrum revealed a reddish hue, consistent with organic compounds or radiation-processed minerals, but nothing diagnostic, no strong absorption features, no emission lines, just a bland reflectance spectrum that could have belonged to any number of solar system bodies. Astronomers hoped for outgassing as the object warmed during its passage near the Sun, hoped for spectroscopic signatures of water vapor or carbon dioxide or methane that would confirm its cometary nature and reveal its composition. But Oumuamua remained silent. No coma formed, no tail extended. The Spitzer Space Telescope searched for thermal emission and found nothing above the noise floor, which placed upper limits on the object's size, probably no more than a few hundred meters across, but didn't solve the mystery of its inactivity. Then came the acceleration. Precise astrometric measurements showed that Oumuamua's trajectory deviated slightly from a purely gravitational path. It was being pushed by something, accelerating away from the Sun at a rate of about 2.5 millimeters per second squared. Comets do this all the time. As their ices sublimate, the escaping gas acts like a tiny rocket engine, nudging the nucleus off course. But Oumuamua showed no detectable outgassing, no gas, no dust, just acceleration. The discrepancy spawned dozens of papers proposing mechanisms. Maybe it was outgassing pure hydrogen, which would be invisible to spectroscopy. Maybe it was venting gas from only one side, creating thrust without a visible coma. Maybe its surface had developed a thick crust that trapped volatiles until they burst out in invisible jets. Or maybe, suggested one astronomer with a taste for provocation, it was something else entirely. An artificial object, a light sail, a probe sent by another civilization. The hypothesis made headlines, triggered debates, and demonstrated how quickly the absence of data invites speculation. Most scientists dismissed the idea not because it was impossible, but because simpler explanations remained unexplored. Extraordinary claims require extraordinary evidence, and Oumuamua provided only ordinary strangeness, the kind of strangeness that sits at the edge of known physics without quite stepping over. The irony is that Oumuamua's weirdness might simply reflect human ignorance. The entire catalogue of cometary knowledge derives from objects born in the solar system. shaped by the sun's radiation and the specific chemistry of the protoplanetary disk that formed 4.6 billion years ago. An object from another star system formed under different conditions, cooled at different rates, experienced different radiation environments during its youth. Its ices might have different structures. Its surface might have accumulated different organic layers. Its internal composition might deviate in subtle but important ways. What looks anomalous might just be foreign, which is not the same as impossible. The scientific community wrote papers, dozens of papers, some invoking exotic physics, others proposing mundane but difficult to test explanations, a few suggesting that Oumuamua wasn't representative of typical interstellar objects, but rather an outlier, a strange edge case that happened to be the first detected simply because it passed close enough to Earth to be visible. The debates continued for months, gradually fading as the object itself faded, dropping below the detection threshold even for the world's largest telescopes. By mid-2018, Oumuamua was gone, billions of kilometers away and too dim to observe. It left behind unanswered questions and a sharpened awareness that the next interstellar visitor might be equally strange. The tumbling haunts the models. Most asteroids and comets rotate relatively quickly. Their spin's the result of collisions or tidal interactions or outgassing torques, but Oumuamua's 8-hour rotation period, combined with its elongated shape, suggests something different. Simulations show that such a configuration is unstable over long timescales unless the object is structurally strong, held together by something more robust than gravity alone. Perhaps it's a fragment of a larger body, sheared off during a collision in its home system. Perhaps it's a shard of planetary crust, ejected during a giant impact. Perhaps its shape isn't even elongated but flat, a pancake tumbling face-on and edge-on, which would also produce the observed brightness variations. The data allows multiple interpretations and excludes none of them. What remains certain is the trajectory. Oumuamua came from the direction of Vega, or rather from where Vega was 300,000 years ago, because stars move and the object's path intersects not with the current positions of stars, but with their past locations. Tracing the orbit backward through time introduces cumulative uncertainties. Gravitational perturbations from planets and passing stars blur the trajectory. After a few million years, the origin becomes untraceable. The object could have been ejected from any of millions of stellar systems within 1,000 light-years. It carries no return address. The departure speed, relative to the local standard of rest, is about 26 kilometers per second, fast enough to escape the solar system, but slow compared to galactic velocities. This suggests the object was likely ejected from its home system at moderate speed, not flung out by a close encounter with a massive planet, but nudged into an escape trajectory by cumulative gravitational interactions. Once free of its star's gravity, it drifted, influenced by the galaxy's gravitational field and the occasional distant tug of other stars. Over millions of years, these small forces added up, altering the trajectory in ways that erased any clear path back to the source. The silence of Oumuamua, no outgassing, no spectroscopic revelations, might be the most frustrating aspect. Comets are talkative. As they warm, they release gas that carries isotopic signatures, molecular abundances, dust particles that reveal the conditions of their formation. A single outgassing comet can provide years of data, spectra that decode the chemistry of the protoplanetary disk, insights into the temperature and pressure and radiation environment billions of years ago. But Oumuamua offered none of this. It passed through the inner solar system in silence, reflecting sunlight but revealing nothing about its interior, its history, or its origin. It was a missed opportunity, or perhaps a reminder that the universe is under no obligation to be legible. The astronomers who studied it published their findings with appropriate caveats. The models remained uncertain. The shape remained ambiguous. The acceleration mechanism remained debated. The object itself, indifferent to all of this, continued outward, climbing away from the Sun at a speed that guaranteed it would never return. By now, it has passed beyond the orbit of Saturn, moving through the outer solar system where sunlight is faint and temperatures hover near absolute zero. In a few more years, it will cross the heliopause, the boundary where the Sun's influence fades and interstellar space begins. And then it will resume the journey it was on before gravity bent its path toward this brief, confusing encounter with human instruments. Only took 300,000 years to get here, give or take, and it didn't stay long enough to explain itself. The second interstellar object arrived with better timing, which is to say it was discovered while still inbound, still approaching the Sun, giving astronomers months to observe instead of weeks. Gennady Borisov, an amateur astronomer in Crimea using a telescope he built himself, spotted it on August 30th, 2019, a faint smudge moving against the background stars. He reported the observation to the Minor Planet Center, which coordinates such discoveries, and within days other observatories confirmed the finding. The orbit was hyperbolic. The eccentricity exceeded 3. This was another visitor from beyond, designated 2I/Borisov, the second confirmed interstellar object, bearing the name of its discoverer. Unlike Oumuamua, Borisov behaved exactly as a comet should. As it approached the Sun, warming under increasing radiation, its surface ices began to sublimate. Water vapor escaped, carrying dust particles into space. A coma formed. A diffuse cloud of gas and dust surrounding the nucleus, glowing softly in reflected sunlight. A tail extended, pushed outward by solar wind and radiation pressure, stretching for millions of kilometers in the direction opposite the Sun. Every telescope on Earth and in orbit turned toward it, capturing spectra, measuring brightness, tracking the evolution of its activity as it swept through the inner solar system. The spectrum revealed familiar signatures. Water vapor, certainly, along with carbon monoxide in abundances similar to solar system comets. The ratio of carbon monoxide to water suggested the object formed in a cold environment, far from its parent star, where CO could condense into ice without being destroyed by stellar radiation. This matched expectations. Comets from the solar system's Oort cloud also show high CO abundances, having formed in the outer regions of the protoplanetary disk before being scattered to distant orbits. The chemistry of Borisov didn't reveal alien compositions or exotic molecules. It revealed ordinariness, the same physics and chemistry that govern object formation around any star. The nucleus itself remained small and difficult to resolve, but estimates placed its diameter at around 1 kilometer, comparable to many solar system comets. Its rotation period, inferred from variations in brightness and coma structure, appeared to be several hours, again within the range of normal cometary behavior. As it approached perihelion, its closest point to the Sun, which it reached in early December 2019, the outgassing intensified. The coma brightened. The tail lengthened. Observers detected subtle changes in the dust color and composition as different ices reached their sublimation temperatures at different distances. Everything made sense. Everything fit the models. The relief among astronomers was palpable, though rarely expressed in scientific papers. After the confounding strangeness of Oumuamua, Borisov offered reassurance that interstellar objects could be understood within existing frameworks. Yes, it came from another star system. Yes, its trajectory was hyperbolic, but its behavior aligned with 4.5 billion years of solar system comet observations. The same thermodynamics, the same sublimation curves, the same relationship between heliocentric distance and gas production rate. The universe, it seemed, did not vary its physics from star to star. Some spectra revealed hints of cyanogen, a molecule often detected in cometary comae, and possibly diatomic carbon. another common cometary species. The dust-to-gas ratio appeared consistent with solar system comets, neither unusually dusty nor unusually gas-rich. Polarimetric observations, which measure how light scatters off dust particles, suggested grain sizes and compositions similar to local comets. Even the dust's color, slightly reddish, indicative of organic compounds, matched expectations. Borisov was, in every measurable way, a normal comet that happened to be visiting from elsewhere. The trajectory analysis told a quieter story. Borisov's velocity relative to the Sun was about 32 kilometers per second, faster than Oumuamua, but still within the expected range for objects ejected from nearby stellar systems. Tracing its orbit backward, astronomers identified a possible origin in the general direction of Cassiopeia, but the uncertainties were large. The object could have been traveling for millions of years, during which time both it and its parent star moved through the galaxy. Pinpointing a specific source system was impossible. The object carried no identifying marks, no chemical fingerprints unique enough to narrow the search to a single star. One subtle detail caught attention. The carbon monoxide abundance relative to water was slightly higher than typical solar system comets, though still within the observed range of long-period comets from the Oort cloud. This might indicate that Borisov formed in an even colder environment than most solar system comets, farther from its parent star where CO remains stable, or it might simply reflect natural variation. Protoplanetary disks are not uniform. Temperature and density gradients create zones where different ices condense. An object formed at one distance will have different chemistry than an object formed slightly farther out or slightly farther in. Borisov's elevated CO could be diagnostic of its formation location, or it could be noise, a statistical fluctuation in a sample size of 1. The brightness evolution followed the expected curve. As the comet approached the Sun, its gas production rate increased exponentially, peaking near perihelion before declining as it moved outward again. Photometric monitoring showed the expected relationship between heliocentric distance and magnitude. Models predicted when the comet would reach maximum brightness, and observations confirmed the predictions within measurement uncertainty. For once, the universe cooperated with human expectations. The outgassing torque, the subtle force exerted by escaping gas, gently altered Borisov's trajectory, as it does for all active comets. The non-gravitational acceleration was small but measurable, and it matched the predictions based on the observed gas production rate. No mysterious accelerations, no unexplained forces, just Newton's laws applied to a sublimating ice ball. The simplicity was almost beautiful. Hubble Space Telescope images resolved the nucleus as a distinct point source separate from the coma, confirming that the object hadn't fragmented despite the thermal stress of passing near the Sun. Some comets break apart during perihelion, torn by tidal forces or internal pressure from sublimating volatiles. Borisov held together. Its structural integrity suggested a cohesive interior. Ices and dust and rock bound by gravity and possibly also by sintering, the process where ices fuse over time under pressure. It was, in this respect, too, unremarkable. The irony, perhaps, is that Borisov's normalcy made it less famous than Oumuamua. The first interstellar object sparked wild speculation, media coverage, debates about alien technology. The second prompted scientific papers, careful measurements, and the quiet satisfaction of confirmation. Both objects were equally interstellar, equally distant from their origins, equally improbable to detect. But only one defied understanding, and defiance captures attention in ways that compliance does not. Borisov faded from view in mid-2020, too distant and too faint for further observation. It left the solar system carrying no mysteries, only data. The models exhaled, the universe made sense, and then, in the quiet aftermath of that relief, The third candidate appeared in the survey data, and the uncertainties began again. The detection networks that scan the night sky for moving objects operate on timescales measured in seconds and terabytes. Every clear night, automated telescopes capture images of the same patches of sky separated by minutes or hours, and software compares them, flagging anything that has shifted position. Most detections are known objects, asteroids in the main belt, near-Earth asteroids on catalogued orbits, distant trans-Neptunian objects creeping through the outer solar system. The algorithms filter out satellites, cosmic rays, instrument artifacts, and background noise, leaving a manageable stream of candidates that human astronomers review each morning. This third WISPR appeared first as an anomaly in the data pipeline from a survey telescope in Chile. The object moved faster than expected for its apparent brightness, and its trajectory didn't match any known asteroid or comet. The automated system flagged it for follow-up. An astronomer reviewed the images, checked the astrometry, the precise measurement of position and motion, and felt the familiar quickening that comes when numbers don't align with expectations. The orbit calculation showed hyperbolic eccentricity. Preliminary, uncertain, but suggestive. The object received a provisional designation, a string of characters encoding the year and the sequence of discovery, not yet confirmed as interstellar, not yet vetted by enough observatories to rule out measurement error or a highly eccentric but still bound orbit. The astronomer sent notifications to colleagues, requested follow-up observations from other telescopes, and began the waiting. Waiting for photons to accumulate, waiting for orbital elements to converge, waiting for confidence intervals to narrow. Other observatories responded. Telescopes in Hawaii, Arizona, the Canary Islands all swung toward the coordinates, capturing the faint point of light against the stellar background. Each new observation refined the orbit. The eccentricity held above 1.0. The velocity relative to the Sun exceeded escape velocity. The trajectory, traced forward and backward through time, showed a hyperbolic arc passing through the solar system just once, never returning. The evidence accumulated slowly, each data point shrinking the uncertainty, until the conclusion became inescapable. This object was interstellar. The third confirmed visitor in 8 years, but the brightness troubled the models from the start. Given its distance from Earth and from the Sun, the object should have appeared brighter if it were the same size and reflectivity as typical comets or asteroids. Either it was smaller than expected, perhaps only a few hundred meters across, or its surface reflected very little light. A low albedo, a dark surface, something that absorbs sunlight instead of scattering it. Spectroscopic observations began as soon as the object was bright enough, though bright is relative. Even with large telescopes and long exposure times, the signal remained faint. The spectral lines blurred and ambiguous. The observers extracted what they could from the data, a featureless continuum. No strong absorption or emission lines, a slightly reddish slope consistent with organic compounds, but not diagnostic. Nothing that matched the clean water ice signatures of solar system comets. Nothing that confirmed or denied the presence of volatiles. Just noise and uncertainty. The confusion deepened when observers searched for a coma. Comets approaching the Sun typically begin outgassing when they cross inside the orbit of Jupiter, where solar radiation warms the surface enough to sublimate water ice. This object had crossed that boundary weeks ago. It should be developing a coma. It should show some hint of activity, some diffuse glow surrounding the nucleus. But the images showed only a point source, sharp and unresolved, indistinguishable from a star except for its motion. No coma, no tail, no gas. The scientists wrote careful emails to each other, hedging their language with appropriate uncertainties. Perhaps the object was simply small, and its gas production rate fell below the detection threshold. Perhaps its surface had developed a thick insulating crust of dust and refractory organics, sealing the ice beneath and preventing sublimation. Perhaps it had been wandering through interstellar space for so long that all its volatiles had already been lost, stripped away by cosmic rays and the gentle warmth of distant stars. All plausible, none testable with the available data. The photometric monitoring continued, measuring the object's brightness every few nights as it approached the sun. A comet should brighten predictably as it gets closer, the increasing solar flux driving more vigorous sublimation and gas production. But this object's brightness curve was shallow, almost flat, brightening more slowly than expected. The discrepancy was small, within the noise for any single measurement, but consistent across multiple observations from different telescopes. Something was wrong, or at least different. One researcher proposed that the object might be intrinsically dark, with an albedo below 5%, absorbing most of the sunlight that hit it and reflecting very little back toward Earth. Such low albedos exist in the solar system. Some carbonaceous asteroids and cometary nuclei are nearly black, but they're rare, and they still show predictable brightening curves. This object's behavior didn't quite match even the darkest solar system analogs. Another hypothesis suggested compositional differences. Perhaps the ices weren't pure water, but some mixture of carbon dioxide, methane, and other volatiles with different sublimation temperatures. Perhaps the object had formed in a region of its birth system where the chemistry differed from the solar system's norm, producing ices that behaved differently under solar heating. But without spectroscopic confirmation, this remained speculation. The data allowed the idea without confirming it. The trajectory refinement continued as more astrometric measurements arrived. The orbit became better constrained. Perihelion, the point of closest approach to the Sun, would occur in approximately 3 months, at a distance of about 1 astronomical unit, similar to Earth's orbital radius. This was close enough that solar heating should drive significant outgassing if any volatiles remained on or near the surface. If the object stayed silent through perihelion, that would be significant, that would be strange. The astronomers submitted observing proposals for time on larger telescopes, on space-based instruments, on spectroscopic facilities that could extract faint signals from noisy backgrounds. The competition for telescope time is fierce, and proposals are judged on scientific merit and feasibility. But an interstellar object passing through the inner solar system makes a compelling case. Opportunities like this arrive once every few years at best, and they don't wait for convenient scheduling. The proposals were approved. The observations were scheduled. The waiting continued. The object moved through space indifferent to all this attention, following the trajectory carved out by gravity and initial conditions, warming slowly as the sun's radiation intensified. If it held volatiles, they remained locked beneath the surface or bound in chemical structures that resisted sublimation. If it was purely rock and refractory organics, it would simply brighten and fade according to geometry and distance, offering no spectroscopic clues, no outgassing signature, no insights beyond its existence. Either way, it continued approaching. A dark visitor from an unknown origin, refusing to fit the categories humans had prepared for it. Only took 8 years for the third one to appear, and already it's being difficult. Brightness in astronomy is measured in magnitudes, a logarithmic scale inherited from ancient Greek astronomers who ranked stars by eye from first magnitude, brightest, to sixth magnitude, faintest visible. The modern system extends this with precision instruments, measuring objects far too dim or too bright for human vision, assigning numbers that encode how many photons reach the detector. A difference of 5 magnitudes equals a factor of 100 in brightness. The faintest objects detected by large telescopes reach magnitude 30 or fainter, billions of times dimmer than anything visible to the naked eye. This object registers around magnitude 20 at its current distance, faint but within reach of medium-sized telescopes with modern CCD cameras. But the absolute magnitude, the brightness it would have if placed at a standard distance from both the Sun and Earth, is fainter than expected. Astronomers calculate absolute magnitude to remove the effects of distance, allowing comparisons between objects regardless of where they happen to be in their orbits. This object's absolute magnitude suggests it is either small, dark, or both. Size estimates depend on assumptions about albedo. If the object reflects 30% of incident sunlight, a typical value for icy bodies, then its diameter is perhaps 300 meters. If the albedo is only 5%, closer to carbonaceous asteroids or cometary nuclei, then the diameter could be twice that, maybe 600 meters. Without direct imaging or thermal emission measurements, the size remains uncertain. The object is too distant and too small to resolve as anything other than a point source, even for the Hubble Space Telescope. The dimness paradox emerges when comparing this object to 2I/Borisov at similar heliocentric distances. Borisov was bright, easily visible in moderate-sized telescopes, its coma contributing significant scattered light. This object shows no coma and appears several magnitudes fainter. If both objects are roughly the same size, then this one must be darker. If they have similar albedos, then this one must be smaller. Or perhaps the comparison is flawed, because Borisov's brightness included contributions from gas and dust, while this object offers only reflected light from its nucleus. Thermal emission provides an independent way to measure size, but it requires infrared observations sensitive enough to detect the faint heat radiated by an object warmed by the sun. The Spitzer Space Telescope, which performs such measurements for Oumuamua, has been retired. The James Webb Space Telescope has the sensitivity but is scheduled months in advance, and securing time for a moving target with uncertain brightness requires proposals, approvals, and careful planning. Observations are planned for later in the object's approach, but for now the size remains an inference layered on assumptions. The surface could be covered in organic tholins, complex carbon compounds created when simpler molecules are irradiated over millions of years. Tholins are dark, reddish-brown, and common on outer solar system bodies like Triton and Pluto, where methane and nitrogen ices are slowly processed by ultraviolet light and cosmic rays. An interstellar object would experience even more intense radiation processing, lacking the sheltering magnetosphere and heliosphere that partially protect solar system bodies. Over geological timescales, this radiation could transform surface ices into a dark, refractory crust that insulates the interior and reduces reflectivity. Laboratory experiments simulate this process by irradiating ice mixtures with ultraviolet light and charged particles, then measuring the resulting spectra and albedos. The products are complex and varied, depending on the initial ice composition, the radiation dose, and the temperature, but they share a common feature. They're darker than the starting material. Virgin ice reflects 60 to 90% of visible light. Irradiated ice, transformed into tholins and other organic residues, might reflect less than 10%. The difference is dramatic and could explain why this object appears so dim, but darkness alone doesn't explain the flat brightness curve. As a comet approaches the sun, even without active outgassing, its brightness should increase according to the inverse square law. Double the solar flux, quadruple the scattered light if the viewing geometry remains constant. This object brightens more slowly, as if some mechanism is suppressing the expected increase. Perhaps the surface is so dark that it absorbs almost all incident light, converting it to heat rather than reflecting it. Perhaps the shape is irregular, and the rotation presents surfaces with varying albedos to the Sun and Earth, smearing out the brightness curve. Perhaps the object is fragmenting slowly, shedding small pieces that fall below detection thresholds but reduce the apparent size of the main body. Fragmentation is common among comets, especially those making their first passage through the inner solar system. Thermal stress from rapid heating can crack the nucleus. Internal pressure from sublimating volatiles can fracture weak spots. Tidal forces from the sun, though negligible for kilometer-sized bodies, can still exert gentle stresses. But fragmentation typically increases brightness temporarily as fresh surface is exposed and small fragments scatter additional light. This object shows no such brightening. If it's fragmenting, it's doing so quietly, without the flares and outbursts that usually accompany cometary breakup. The albedo problem extends to spectroscopy. A dark surface absorbs most wavelengths of light, leaving little signal for spectrographs to analyze. The faint reflected light must be spread across multiple wavelengths to extract compositional information, and spreading signal reduces the signal-to-noise ratio in each spectral channel. The observers are trying, exposing for hours, stacking multiple images, applying sophisticated data reduction techniques. But the spectra remain noisy, ambiguous, dominated by statistical fluctuations rather than clear absorption or emission features. One spectrum hints at a shallow absorption band near 1 micron wavelength, possibly consistent with silicate minerals or pyroxene. Another shows a slight reddening toward longer wavelengths. The spectral slope that often indicates organic compounds. But these features are weak, barely rising above the noise. And different observatories report slightly different results. The spectral signature is either genuinely featureless or so faint that current instruments can't extract it reliably. Either way, the object refuses to speak clearly. Photometric models attempt to predict brightness based on shape, rotation, and albedo. Researchers input various assumptions: spherical nucleus, elongated nucleus, tumbling rotation, stable rotation, and compare the model outputs to observations. None fit perfectly. The data can be accommodated by adjusting parameters, but the adjustments push toward unusual values: very low albedo, very slow rotation, irregular shape with high amplitude brightness variations. The models work, technically, but they require the object to be an outlier, sitting at the edge of the distribution of known properties. The astronomers writing these papers are careful with their language. They describe the object as challenging current models, or exhibiting unusual photometric behavior, avoiding stronger claims without stronger evidence. Science proceeds slowly, accumulating observations, testing hypotheses, allowing the data to constrain interpretations. The object will either reveal itself as it approaches perihelion, or it will remain enigmatic, adding another data point to the small and confusing sample of interstellar visitors. The dimness persists, a quiet defiance of expectation. The object absorbs sunlight and returns almost nothing, moving through the inner solar system like a shadow, visible only because even shadows can be measured if the instruments are sensitive enough. Only took billions of years to form, and it still won't reflect properly. Spectroscopy decodes light by splitting it into constituent wavelengths, revealing the fingerprints of atoms and molecules. When sunlight reflects off an object, certain wavelengths are absorbed by chemicals on the surface or in any surrounding gas. The reflected light, now missing those specific wavelengths, carries an absorption spectrum, a pattern of dark lines or bands superimposed on the continuum. Different molecules absorb at different wavelengths. Water ice absorbs strongly in the infrared around 3 microns. Carbon dioxide ice shows bands near 2 and 4 microns. Silicate minerals create broad, shallow features in the visible and near infrared by matching observed spectra to laboratory measurements. Astronomers infer composition without ever touching the object. This object's spectrum defies simple matching. The observations, collected over multiple nights by different telescopes, show a red-sloped continuum, brightness increasing toward longer wavelengths, but few clear absorption features. A possible shallow band near 1 micron might indicate pyroxene, a common silicate mineral found in asteroids and rocky planets. A hint of absorption near 2 microns could be water ice, but the feature is weak and ambiguous, barely distinguishable from noise. No strong signature of carbon dioxide, no methane, no ammonia, no organic bands diagnostic of complex carbon chemistry, just a featureless slope that tells almost nothing. The redness itself is information, or at least suggestive. Many outer solar system bodies exhibit red surfaces due to organic compounds created by radiation processing of methane and other volatiles. Centaurs, objects orbiting between Jupiter and Neptune, often show red colors. Some trans-Neptunian objects are deeply red, their surfaces rich in tholins and other complex organics. But redness is a generic feature, not a unique identifier. Dozens of processes can produce reddish slopes in reflectance spectra, and without additional spectral features to narrow the possibilities, the redness constrains almost nothing. Carbonaceous materials could explain the darkness and the spectral slope. Carbonaceous chondrites, a class of primitive meteorites, contain organic compounds and hydrated minerals that together produce dark, reddish surfaces. Their albedos range from 3 to 10%. Their spectra show the same kind of featureless red slope observed in this object. If the interstellar visitor is compositionally similar to carbonaceous asteroids, rich in carbon, poor in volatiles, processed by radiation, then its spectrum makes sense. But this interpretation assumes the object is essentially a dark rock, not an icy comet, which raises the question of how it was ejected from its birth system. Rocky objects form in the inner regions of protoplanetary disks, where temperatures are too high for ice to condense. Icy objects form farther out. Ejection mechanisms work best in the outer regions, where gas giants can gravitationally scatter smaller bodies to high velocities. A rocky interstellar object is not impossible, but it's less expected. Models of protoplanetary disks predict that most ejected objects should be icy, formed beyond the snowline where water ice is stable. These icy bodies, scattered by migrating giant planets, constitute the majority of the interstellar population according to simulations. Rocky bodies can also be ejected, but they require closer encounters with planets, more specific orbital configurations, and they should be rarer. If this object is rocky, it might be statistically unusual, or the models might underestimate the ejection rate of rocky material, or the classification itself might be wrong, and the object holds ice beneath a dark crust. The spectroscopic templates used for comparison come from solar system objects, measured over decades with increasingly sophisticated instruments. Water ice on comet surfaces produces sharp absorption bands in the near-infrared. These bands have been measured hundreds of times, their wavelengths and shapes well characterized. The absence of such bands in this object's spectrum means either there's no water ice on the surface, or the ice is covered by something opaque, or the ice is present in forms that don't produce diagnostic absorption features. Amorphous ice, disordered at the molecular level, shows weaker and broader absorption bands than crystalline ice. Contaminated ice, mixed with dust or organics, can have its spectral features diluted to the point of invisibility. Temperature affects spectra as well. Colder ice has sharper absorption features. Warmer ice, approaching its sublimation temperature, shows broader and weaker bands. This object, still months away from perihelion, remains cold. Surface temperatures are likely below 150 Kelvin, cold enough to keep water ice stable. But if the surface is covered by a dark layer of refractory organics, that layer absorbs sunlight and warms above the ice beneath, creating a temperature gradient that might suppress ice signatures in the reflected light spectrum. Compositional models feed into thermal models that predict how the object should warm as it approaches the sun. Heat deposited at the surface conducts inward, raising subsurface temperatures and potentially triggering sublimation beneath the crust. If pressure builds up, the crust might crack, releasing gas in sudden outbursts. Comets sometimes exhibit such behavior, quiescent for long periods, then suddenly brightening as a section of crust fails and fresh ice is exposed. But predicting when or if this will happen requires knowing the crust thickness, its thermal conductivity, its mechanical strength, all unknowns for this object. The spectrum has been compared to databases containing thousands of entries. Asteroids, comets, trans-Neptunian objects, meteorites, laboratory samples of minerals and ices. No perfect match emerges. Some objects show similar red slopes, some have comparable albedos, but none match across all measured properties. The closest analogues are perhaps certain D-type asteroids in the outer main belt, dark and red, possibly coated with organic material from early solar system chemistry. But D-type asteroids are solar system natives, formed locally, not interstellar visitors. The analogy is imperfect. Observers have also searched for emission lines that would indicate gas production. When molecules like water or carbon monoxide are released from a comet's surface and heated by sunlight, they emit light at characteristic wavelengths. These emission lines appear bright against the dark sky background, easier to detect than absorption features in reflected sunlight. But the searchers have returned nothing. No hydroxyl emission, which would indicate water dissociation, no CN or C2 emission, common signatures of carbon-bearing molecules in cometary comae, no sodium D-line emission, sometimes seen when dust particles are heated to high temperatures. The object emits nothing detectable, remaining spectroscopically silent. The fracture in compositional models becomes apparent when researchers try to reconcile all the observations simultaneously. The dark surface suggests carbonaceous composition or radiation-processed organics. The lack of outgassing suggests either no volatiles or volatiles trapped beneath an impermeable crust. The red spectral slope suggests complex organic compounds. The faint brightness suggests small size or very low albedo. But building a single coherent model that explains all these features without invoking special circumstances proves difficult. Each model requires assumptions that feel slightly arbitrary, tuned to fit the data rather than emerging naturally from first principles. One possibility is that the object represents a new class of interstellar body, something not present in the solar system's inventory. Perhaps stars with different metallicities, different abundances of elements heavier than hydrogen and helium, produce protoplanetary disks with distinct chemistry. The solar system formed from a molecular cloud enriched by multiple generations of stellar nucleosynthesis, containing roughly solar abundances of carbon, nitrogen, oxygen, and heavier elements. A star formed from a cloud with different enrichment history might produce planets and planetesimals with different mineral and ice compositions. An object ejected from such a system could have spectral properties unfamiliar to solar system astronomers. But invoking exotic chemistry without strong evidence is premature. The sample size of interstellar objects remains 3, possibly 3, and drawing conclusions about diversity from such a small sample invites overfitting. Variation exists within the solar system itself. Different asteroid families have different compositions. Different comets show different volatile abundances. The interstellar population should also vary. This object might simply represent one tail of the distribution. Unusual, but not impossible. Strange, but not alien in the sense of requiring new physics. The spectroscopic ambiguity leaves the object undefined in the taxonomy that astronomers use to categorize small bodies. It's not clearly a comet, lacking outgassing and a coma. It's not clearly an asteroid, given its interstellar origin and possible volatile content. It exists in a liminal category, neither one thing nor another, defined primarily by what it lacks rather than what it exhibits. The classification will likely remain ambiguous until more data arrives. If more data arrives, if the object chooses to reveal anything at all before it fades beyond observation, the chemistry remains locked inside, shielded by the dark surface that reflects almost nothing and absorbs almost everything. The atoms and molecules that record the conditions of formation, the temperature and pressure and radiation environment of a distant protoplanetary disk remain inaccessible to spectroscopy. They sit beneath the surface, beneath the crust, in the cold interior where photons never reach and instruments cannot probe. The object keeps its secrets, offering only hints and ambiguities, refusing to fit the templates built from solar system experience. Only took millions of years to drift here, and it won't say where it came from. Gas production from comets follows predictable patterns verified by decades of observation and centuries of theory. As a comet approaches the sun, solar radiation heats its surface. When surface temperatures rise above the sublimation point of volatile ices, around 150 Kelvin for water ice, lower for carbon monoxide and other species, those ices transition directly from solid to gas without passing through a liquid phase. The escaping gas molecules carry dust particles with them, creating the diffuse coma and extended tail that make comets visible even when their nuclei are too small to resolve. This object shows none of this activity. At its current heliocentric distance, slightly beyond Earth's orbit and closing, surface temperatures should have risen above the water-ice sublimation threshold weeks ago. If the surface contained exposed water ice, gas should be escaping. If the ice is buried beneath a thin layer of dust, thermal conduction should have warmed the subsurface enough to trigger some sublimation. But the images show no coma, no extended emission, just a point source that might be a bare nucleus or might be something else entirely. The outgassing models depend on several factors: the composition of the surface, the thermal conductivity of the material, the porosity of the crust, the depth to volatile rich layers. For typical solar system comets, these parameters are reasonably well constrained by observations of many objects over many orbits. Water ice dominates. Thermal conductivity is low because cometary material is porous, filled with voids that inhibit heat transfer. Dust mantles develop as sublimation removes volatiles, leaving behind a lag deposit of refractory particles that insulates the ice beneath. But these parameters derive from local experience. An interstellar object might differ in subtle but important ways. Perhaps the porosity is different. Perhaps the object formed in a colder environment where sintering, the fusing of ice grains under pressure, proceeded more efficiently, creating a denser structure with higher thermal conductivity. Heat would penetrate deeper, warming larger volumes, but also escaping more readily, preventing the temperature from rising high enough to drive vigorous sublimation. The surface would warm, but the subsurface would remain cold. Locked in thermal equilibrium that keeps volatiles stable. Or perhaps the volatiles are simply absent. Not all small bodies contain ice. Asteroids in the inner solar system are rocky and dry. They're volatiles driven off during formation or by prolonged exposure to solar radiation. If this object formed in the inner region of its birth system, where temperatures exceeded the ice sublimation threshold, it might never have contained water ice. It would be a rocky fragment, compositionally similar to Earth's crust or Mars's surface, ejected into interstellar space by some violent process. Giant impacts can eject material at high velocities. Close encounters with planets can scatter rocky debris. The mechanism exists, even if it seems less probable than the ejection of icy bodies from outer system regions. The whisper of outgassing, if it exists at all, falls below current detection thresholds. Gas production rates are measured by observing emission lines from molecules excited by sunlight or by detecting the coma's scattered light in broadband images. The sensitivity of these measurements depends on telescope size, exposure time, and background noise. For a faint object far from Earth, the detection limit might be around 10 to the 26 molecules per second, roughly a thousandth the gas production rate of a moderately active comet. If this object is producing gas at rates below this threshold, it would appear inactive even though sublimation is occurring. Alternatively, the outgassing might be highly asymmetric, concentrated in small active areas that cover only a tiny fraction of the surface. Some comets exhibit such behavior. Most of the nucleus remains inactive, covered by a thick dust mantle, while a few localized vents release most of the gas. If the active areas face away from Earth or toward the Sun at angles that make the coma difficult to observe, the outgassing could be missed. The geometry of observation matters. A faint coma viewed edge-on appears brighter and more extended than the same coma viewed pole-on. The object's rotation, its orientation in space, its position relative to Earth and the Sun, all these factors influence what observers detect. The lack of a dramatic tail eliminates one diagnostic tool. Comet tails form when solar wind and radiation pressure push gas and dust away from the coma, creating streams that extend for millions of kilometers in the anti-solar direction. The tail's shape and brightness reveal information about gas and dust production, particle sizes, and the interaction between the coma and the solar wind. But this object offers no tail, no extended structure, nothing to analyze beyond the unresolved point source. It whispers where others scream. Non-gravitational forces complicate the trajectory analysis. When a comet outgasses asymmetrically, more gas escaping from the sunward side, or from one hemisphere due to rotation, the momentum carried away by the gas exerts a small force on the nucleus. This force, called the rocket effect, slightly alters the orbit over time. Precise astrometric measurements can detect these non-gravitational accelerations, and from them, astronomers infer gas production rates even when direct observation of the coma is difficult. Oumuamua showed such acceleration without visible outgassing, creating the mystery that spawned dozens of papers. This object has been tracked for weeks now, and the astrometric data shows ambiguity. Some analyses suggest a tiny non-gravitational acceleration, a deviation from a purely Keplerian orbit that would be consistent with low-level outgassing. Other analyses, using different datasets or different statistical methods, find no significant deviation within the measurement uncertainties. The signal, if real, is at the edge of detectability, buried in noise, requiring more data and longer baselines to confirm or refute. The uncertainty is frustrating, but not unusual. Small forces acting on small objects produce small perturbations that take time to accumulate into measurable effects. If the acceleration is real, it implies gas production too faint to detect directly, but strong enough to nudge the orbit. This would suggest that sublimation is occurring beneath the surface or in localized areas, releasing gas at rates below the coma detection threshold, but sufficient to exert measurable force. The object would be technically active. Even though it appears inert, the classification would shift from inactive to weakly active, a subtle distinction with significant implications for models of interstellar object composition. If the acceleration is noise, an artifact of measurement error, or unmodeled perturbations from planetary gravity fields, then the object is truly inactive, coasting through the inner solar system without releasing gas, without responding to solar heating, as inert as a rocky asteroid. This would make it unusual among comets, but not unprecedented. Some solar system comets have become dormant, their surface ices exhausted or sealed beneath thick dust mantles, leaving only the refractory nucleus visible. The object might represent a similar endpoint. exhausted by time and interstellar radiation rather than by repeated passages near the Sun. The outgassing paradox, acceleration without visible gas, or no acceleration and thus no gas, mirrors the paradox of Oumuamua. Both objects refuse to fit cleanly into categories. Both exhibit behavior that sits at the boundary between comet and asteroid, active and inactive, ordinary and strange. The universe seems to enjoy sending humans edge cases, objects that test the limits of classification schemes built from limited samples. The models predict that perihelion will be the critical test. As the object reaches its closest approach to the Sun, solar flux will peak, surface temperatures will rise to their maximum, and any remaining volatiles should sublimate if they're going to sublimate at all. If the object stays silent through perihelion, the case for a volatile depleted composition strengthens. If it suddenly brightens, developing a coma and tail, the models exhale and mark it as a normal comet that was simply slower to wake than expected. The waiting continues, the telescopes continue monitoring, and the object continues approaching, indifferent to the questions it provokes, only took interstellar travel to avoid outgassing like everything else. The trajectory of any object through space is determined by gravity and initial conditions, modified over time by non-gravitational forces if such forces exist. For interstellar visitors, the hyperbolic orbit passes through the solar system once, bending around the Sun in a graceful arc before climbing back out toward the stars. The precise shape of this orbit, its eccentricity, inclination, perihelion distance, encodes information about the object's velocity at infinity, the speed it would have if the Sun's gravity were removed. This velocity, typically 20 to 40 kilometers per second for detected interstellar objects, represents the object's motion relative to the local standard of rest, the average velocity of stars in the Sun's galactic neighborhood. This object's trajectory, refined over weeks of observation, shows an eccentricity of approximately 1.2, clearly hyperbolic. The inclination is modest, about 15 degrees relative to the ecliptic plane, meaning the object's path is not dramatically tilted compared to the planetary orbits. Perihelion will occur at roughly 1 astronomical unit from the Sun, close to Earth's orbital distance, though the object itself will be on the far side of the Sun at that time, not particularly near Earth. After perihelion, the trajectory curves outward, steepening as the object accelerates away from the Sun's gravity well, eventually departing at an angle that will carry it above the galactic plane over the next few million years. But the trajectory shows hints of something unexpected, something that emerges only when the most precise astrometric measurements are analyzed with sophisticated orbital models. The deviation is tiny, measured in arc-seconds over weeks of observation, but it's persistent. The object is not following a perfect Keplerian orbit defined solely by the Sun's gravity. Something else is acting on it, a small force producing a small acceleration. And the magnitude and direction of this force don't match the expected signature of outgassing. Non-gravitational accelerations from outgassing typically point away from the Sun, or slightly off the radial direction due to rotational lag, the delay between when a surface element faces the Sun and when the sublimation-driven gas escapes. This object's anomalous acceleration, if the analysis is correct, points in a direction that doesn't align neatly with the solar vector. The angle is wrong. The timing is wrong. The magnitude, while consistent with low-level gas production, appears decoupled from the object's distance from the Sun in ways that standard outgassing models don't predict. Several researchers have attempted to model this anomalous force. One suggestion involves asymmetric outgassing from an irregularly shaped nucleus with complex rotation. If the object tumbles chaotically, rather than spinning around a stable axis, and if active areas are located in specific regions of the surface, the net force from escaping gas could point in almost any direction. The time-averaged acceleration would depend on the rotation period, the distribution of active spots, and the thermal inertia of the surface material. This model is flexible enough to accommodate almost any observed acceleration, which makes it unfalsifiable and therefore not particularly useful. Another model proposes that the object is fragmenting slowly, shedding small pieces that carry away momentum. When a comet nucleus breaks apart, the fragments exert forces on each other through mutual gravity and through collisions with escaping gas. If the fragmentation is gradual and asymmetric, it could produce non-gravitational accelerations that don't follow the standard outgassing pattern, but no fragments have been detected around this object. Searches for companion pieces, objects following similar orbits, have found nothing. If fragmentation is occurring, it's at scales too small to observe, or the fragments are too faint, or they don't exist. A third possibility involves thermal effects unrelated to sublimation. The Yarkovsky effect causes small objects to experience gentle forces due to anisotropic thermal emission. An asteroid absorbs sunlight on its day side and re-radiates that energy as infrared photons hours later after the surface has rotated. The emitted photons carry momentum, and the delay between absorption and emission creates a net force that can slowly alter the orbit for kilometer-sized objects. The Yarkovsky effect is small but measurable over years or decades. For this object, the effect might be significant given its apparently low albedo and possibly slow rotation, both of which enhance thermal emission asymmetry. But calculating the Yarkovsky force requires knowing the object's size, shape, rotation rate, thermal inertia, and surface roughness, all uncertain or unknown. The models can be adjusted to produce almost any desired acceleration magnitude, making predictions circular. The observation suggests a force. The models require parameters. The parameters are chosen to match the force. The result confirms nothing except that the math works. The paradox deepens when considering the lack of visible outgassing. Standard cometry models link non-gravitational acceleration directly to gas production. More gas means more force. The relationship is nearly linear for simple geometries. But this object shows acceleration without detectable gas, the same puzzle that haunted Oumuamua. Proposals to explain Oumuamua's acceleration involved exotic ideas like hydrogen icebergs or thin light sails, mechanisms that would produce thrust without visible coma. Most of these ideas were later shown to be physically implausible or inconsistent with other observations. The mystery of Oumuamua's acceleration remains unresolved, and now this object appears to present the same mystery again. One subtle difference: the acceleration magnitude for this object, if real, is smaller than Oumuamua's, closer to the detection threshold. It's possible that better data, or longer baselines, will reveal the acceleration to be noise, an artifact of measurement errors or unmodeled perturbations from planets, the asteroid belt. Though sparse, exerts cumulative gravitational influences on objects passing through. Jupiter's gravity, even at large distances, creates perturbations. Earth and Venus pull gently on nearby objects. All these forces must be modeled correctly to extract the tiny signal of non-gravitational acceleration from the data. Mistakes are easy. Certainty is hard. The trajectory will continue to refine as more observations accumulate. Each new position measurement shrinks the uncertainty ellipse around the predicted orbit. Given enough data, the anomalous acceleration will either emerge clearly from the noise or disappear into it, recognized as a statistical fluctuation. But that clarity won't arrive for weeks or months, long after the object has passed perihelion and begun its outward journey. By the time the orbit is known precisely, the object may be too faint for spectroscopy or detailed imaging, leaving questions unanswered even as the trajectory is nailed down. The predictions based on current data show the object departing the solar system at roughly 30 kilometers per second, relative to the Sun, slightly faster than its inbound velocity due to the gravitational acceleration during its close pass. It will climb outward through the planetary orbits, passing Mars, Jupiter, Saturn, each at distances measured in astronomical units, crossing the heliopause, the boundary of the Sun's influence, in a few decades, and then back into interstellar space, resuming the million-year drift that was briefly interrupted by this encounter with human instruments. The orbit, hyperbolic and one-time, ensures that humans will never see this object again. No future apparition, no return visit. This passage through the inner solar system is unique, a singular intersection of trajectories that will not repeat. The data collected now is all the data there will ever be. The measurements, the spectra, the images, this is the complete record, and it will have to suffice. Whether or not it answers the questions, the motion continues. Predictable in the large-scale sense, but uncertain in the details, carrying the object toward perihelion and the maximum heating that will either trigger activity or confirm inertness. The acceleration, anomalous or illusory, persists in the data, a whisper of force that might mean something or might mean nothing, waiting for more photons to clarify or confound. Only took precise astrometry to reveal the uncertainty, and the uncertainty refuses to resolve. The database of cometary knowledge spans centuries, beginning with naked eye observations of bright comets recorded by ancient civilizations and extending through the telescopic era into the age of spacecraft and space-based observatories. Thousands of comets have been catalogued, their orbits calculated, their brightnesses monitored as they approach and recede from the Sun. The data fills archives, photographic plates from the 19th century, digital images from modern surveys, spectroscopic observations revealing gas composition, spacecraft flybys providing close-up views of nuclei. This accumulated knowledge forms the basis for models that predict how comets should behave. The models are empirical, built from observation rather than derived purely from theory. They encode relationships discovered through statistical analysis of large samples. Brightness versus heliocentric distance follows a power law, with typical exponents around -4 for dusty comets and -2 for gas-dominated ones. Gas production rates scale with the nucleus's cross-sectional area exposed to sunlight. Dust-to-gas ratios vary, but cluster around unity for most comets. These patterns, verified across hundreds of objects, are assumed to apply universally because they reflect fundamental physics, thermodynamics, sublimation kinetics, radiation transport. But the database contains only solar system objects. Every measured comet, every asteroid, every trans-Neptunian object formed from the same protoplanetary disk 4.6 billion years ago. They share common chemistry, common initial conditions, common evolutionary histories shaped by the Sun's radiation and the planet's gravity. The models built from this data implicitly assume that interstellar objects obey the same patterns, that the physics of sublimation and light scattering and orbital mechanics applies identically to visitors from other star systems, and for 2 I/Borisov. This assumption held perfectly. The comet behaved exactly as the database predicted. This object does not. It sits outside the distribution of measured properties, an outlier in brightness, in spectral features, in outgassing behavior. The models can be stretched to accommodate it, parameters adjusted, special circumstances invoked, but the fit remains uncomfortable. The object is not impossible according to the models, but it's improbable, residing in the tails of the distributions where few data points exist and uncertainties grow large. One way to visualize this is through parameter space, a multi-dimensional framework where each axis represents a measurable property: albedo, size, gas production rate, dust-to-gas ratio, spectral slope, rotation period. Solar system comets populate certain regions of this space, clustering around typical values. A few outliers extend into less populated regions, unusual objects with extreme properties. This interstellar object occupies a region sparsely populated or entirely empty in the solar system catalog. It exists in parameter space, certainly, but at a location that solar system experience rarely touches. The question becomes whether this reflects genuine differences between interstellar and solar system populations, or simply the fact that the interstellar sample size is tiny. 3 confirmed objects, maybe 3, is not enough to define a population. Statistical inference requires dozens of samples at minimum, hundreds for robust conclusions. With 3, nearly anything can happen and look like a pattern. Random variation can masquerade as systematic difference. The outlier nature of this object might be noise, the inevitable result of small number statistics. But the outlier nature might also be signal. Perhaps objects from other stellar systems do differ systematically from solar system bodies. Stars with different metallicities produce protoplanetary disks with different compositions. Stars with different luminosities heat their disks differently, altering the radial distribution of ice lines and the chemistry of condensing solids. A planet formed around a dim red dwarf has different volatile content than a planet formed around a bright blue star. An object ejected from one of these systems carries the chemical signature of its origin, and that signature might not match solar system norms. The database can't distinguish between these possibilities. It contains what it contains: local data, local objects, local chemistry. Extending its applicability to extrasolar objects is an assumption, reasonable but untested. And this object tests it by not fitting comfortably. The models say it should be brighter, or it should be outgassing, or it should show spectral features diagnostic of water ice. The object declines all of these suggestions, offering instead a dark, quiet surface that reflects little and emits nothing detectable. Comparison with Oumuamua is inevitable but complicated. Both objects are dark, both show minimal or no outgassing. Both exhibit possible non-gravitational accelerations that don't match standard comet models. But Oumuamua's light curve suggested an elongated shape, while this object's brightness variations, if they exist, are subtle and don't clearly indicate extreme elongation. Oumuamua moved much faster. Its hyperbolic excess velocity nearly double this object's. Oumuamua was discovered outbound, already past perihelion, while this one is still approaching. The differences are at least as significant as the similarities. Establishing a taxonomy of interstellar objects requires more samples. Do they fall into discrete classes, icy comets like Borisov, inert bodies like Oumuamua and possibly this one? Or do they span a continuum, with properties varying smoothly based on formation conditions and evolutionary history? The solar system's small bodies exhibit both patterns. Asteroids and comets form reasonably distinct classes, but objects like main belt comets and active asteroids blur the boundary. Trans-Neptunian objects show continuous variation in color and albedo rather than discrete types. The interstellar population might be similarly complex, and 3 samples can't reveal that complexity. The database grows slowly. 1 detection every few years. Survey telescopes are getting better, more sensitive, covering larger areas of the sky more frequently. The Vera Rubin Observatory, currently under construction, will survey the entire visible sky every few nights, detecting faint moving objects that current surveys miss. It should find multiple interstellar visitors per year once operational. The sample size will grow from 3 to 30, then to hundreds over a decade. The parameter space will fill in. The outliers will either cluster into new populations or spread randomly, revealing whether patterns exist. But for now, the database contains 3 entries, possibly 3, and each one is strange in its own way. Borisov made sense. Oumuamua did not. This object, currently under observation, does not. The ratio of strange to normal is 2:1, or possibly 3:0 if Borisov turns out to be the outlier. The unusually cooperative visitor that gave false confidence about predictability. The statistics are too poor to conclude anything except that conclusions are premature. The comparison extends beyond the solar system to theoretical predictions. Simulations of planet formation and dynamical evolution predict how many small bodies should be ejected from typical stellar systems and what their properties should be. These models, run on supercomputers tracking millions of particles over billions of years, suggest that icy bodies from the outer regions should dominate the interstellar population. Rocky bodies should be rarer. The density of interstellar objects passing through the inner solar system should be around 1 per year for objects larger than 100 meters. Detection rates depend on survey sensitivity and sky coverage, but with current telescopes, astronomers expected to find one interstellar visitor every few years. The detection rate so far matches predictions roughly. 3 objects in 8 years is close to expectations, though the uncertainties are large enough that the actual rate could be half or double the predicted value. But the properties of the detected objects don't match predictions as well. The models didn't anticipate dark, inactive bodies like Oumuamua. They expected more Borisov-like comets, bright and outgassing, easily distinguishable from solar system objects. The universe delivers what it delivers, indifferent to expectations. The database awaits more data, more objects, more photons accumulating in detectors night after night. The models await refinement, parameters updated to match observations rather than predictions. And this object, this third whisper from beyond, awaits perihelion, the moment when solar heating peaks and the last chance for activity arrives, when it will either fit the categories prepared for it or refuse once more. Only took 4.5 billion years to build the database, and it's still incomplete. Dark matter does not hide in small objects. The mystery of dark matter, the gravitational evidence for mass that doesn't emit light, that doesn't interact electromagnetically, that seems to outweigh visible matter by a factor of 5, operates on galactic and cosmological scales. Dark matter halos surround galaxies, their gravity shaping the rotation curves of stars and gas. Dark matter filaments connect galaxy clusters, their gravitational lensing distorting the light from distant sources. But dark matter doesn't clump into kilometer-sized bodies. The physics that allows dark matter to form large-scale structures prevents it from cooling and condensing into small, dense objects. It remains diffuse, smooth, pervasive but not concentrated. This object is ordinary matter, baryonic, as physicists say, composed of protons and neutrons and electrons, the same particles that make up everything familiar. Its darkness is optical, not ontological. It appears dark because its surface reflects little light, not because it's made of exotic particles that don't interact with photons. The darkness is chemistry and geometry, not fundamental physics. And yet, the darkness invites questions, the kind of questions that arise when observations don't match expectations, when the usual explanations require stretching. The composition, whatever it is, formed in a protoplanetary disk around a star that existed millions or billions of years ago. That star might still exist, might still be shining somewhere in the galaxy, unidentifiable among billions of similar stars. Or it might have died, collapsed into a white dwarf, or exploded as a supernova, leaving no trace except the debris it scattered. The object carries no memory of its parent star, no identification that would allow astronomers to trace it back to a source. It's anonymous, orphaned, severed from its origin by time and distance. The chemistry of that disk depended on the star's metallicity, the abundance of elements heavier than hydrogen and helium. Stars formed early in galactic history, from gas clouds enriched only by the first generation of supernovae, have low metallicity. Their planets and planetesimals contain less carbon, less oxygen, less silicon and iron than solar system bodies. Stars formed more recently, from clouds enriched by multiple generations of stellar nucleosynthesis, have higher metallicities, approaching or exceeding the Sun's values. The object's chemistry encodes its birth environment's metallicity, but spectroscopy hasn't revealed that chemistry clearly enough to infer metallicity. If the object formed in a low metallicity environment, its ices might contain less carbon dioxide and methane relative to water than solar system comets. Its rocky component might be poorer in iron and silicates. The radiation processing of such material over millions of years would produce different organic compounds, different surface colors, different spectral slopes, but without detailed spectroscopy. These remain speculation. The chemistry is locked inside, inaccessible. The radiation environment of interstellar space is harsher than the environment inside a stellar system. Cosmic rays, high-energy particles accelerated by supernova shockwaves and other violent events, pervade the galaxy. They strike any object in their path, penetrating centimeters into the surface, breaking chemical bonds, creating radicals and new molecules, slowly transforming the composition. Inside the solar system, the Sun's magnetic field and solar wind deflect some cosmic rays, reducing the flux. Outside the solar system, in the true interstellar medium, the cosmic ray flux is higher by a factor of several. An object wandering through interstellar space for millions of years accumulates radiation damage that solar system objects never experience. Laboratory experiments simulate this by irradiating ice samples with protons and heavy ions, mimicking cosmic rays, then measuring the resulting chemistry. The products include complex organic molecules, long carbon chains, aromatic compounds, all created by the slow destruction and recombination of simpler starting materials. Over geological time, these processes can convert a pristine, icy surface into a dark, organic-rich crust centimeters thick. The crust acts as insulation, protecting the interior from further radiation, but also preventing sublimation when the object later approaches a star. This object's dark surface might be such a crust, the accumulated product of millions of years exposed to cosmic rays and the faint ultraviolet light of distant stars. If so, the interior could still be pristine, icy and chemically unaltered, locked in the state it held when it was ejected from its birth system. But the interior is inaccessible. Only the surface can be observed, and the surface is dark, processed, transformed into something that doesn't match the spectroscopic templates of fresh ice or bare rock. The questions multiply without dark matter to invoke, without exotic physics to simplify. Ordinary matter, ordinary processes, but parameters and conditions outside the range sampled by solar system objects. The object doesn't require new science, but it might require expanding the parameter space of existing science, acknowledging that the range of compositions and evolutionary paths is broader than local experience suggests. One researcher proposes that the object might be a fragment of a destroyed planet, shattered by a collision or torn apart by tidal forces during a close encounter with a star or massive planet. Planetary material differs from primordial planetesimal material. It has been heated, differentiated, chemically evolved by geological processes. The crust of a terrestrial planet is mostly silicates and feldspars, dark when powdered and lacking volatiles. A fragment of such crust, ejected into space, would look dark and rocky, with no ices to sublimate. The spectroscopy might match, the low albedo might match, the inactivity might match. But ejecting planetary fragments into interstellar space requires violent events, catastrophic impacts, or extreme tidal disruption. Such events are rare, Most planet formation simulations predict that the vast majority of ejected objects are planetesimals, small bodies from the outer disk, not fragments of shattered planets. The planetary fragment hypothesis can't be ruled out, but it invokes a low probability event to explain one object, which feels like special pleading. Another idea involves captured objects from the interstellar medium, bodies that formed not in protoplanetary disks, but in the diffuse gas of molecular clouds. Some theories suggest that turbulence and gravitational instabilities in molecular clouds can create small, dense cores that collapse into objects too small to ignite fusion, too small even to qualify as brown dwarfs. These sub-brown dwarfs would be dark, cold, composed of hydrogen and helium with traces of heavier elements, drifting through the galaxy undetected. But such objects would be much larger than this visitor, and their composition wouldn't match the hints of silicates and organics in the spectrum. The idea is creative but doesn't fit. The questions that don't require dark matter are still questions. The object's composition remains uncertain. Its formation environment remains unknown. Its evolutionary history, the processes that shaped its surface and interior over millions or billions of years, can only be guessed. The darkness is ordinary, but the origins of that darkness are not yet understood. The object refuses to explain itself in the language astronomers speak, refuses to show the spectral features that would decode its past, content to drift through the solar system as it drifted through the interstellar space, silent and unrevealing. Only took ordinary physics to create it. But ordinary physics allows many possibilities, and the data hasn't narrowed them yet. Albedo measures reflectivity, the fraction of incident light that an object scatters back into space rather than absorbing. Fresh snow has an albedo near 90%, reflecting almost all visible light, which is why it appears brilliant white. Charcoal has an albedo near 5%, absorbing most light, appearing black. Planetary bodies span this range. Enceladus, Saturn's icy moon with a fresh surface of water ice, has an albedo near 100%. The moon's rocky, dusty surface has an albedo around 12%. Cometary nuclei, coated with dark organic compounds and dust, typically have albedos between 4 and 8%, darker than charcoal. This object's albedo, inferred from its faintness and estimated size, appears to be in the low single digits, possibly below 5%. This places it among the darkest objects in the solar system, comparable to certain carbonaceous asteroids or the nuclei of exhausted comets. But the uncertainty is large. If the object is smaller than current estimates, the albedo could be higher. If it's larger, the albedo drops even further, approaching values so low they challenge explanations. The albedo problem manifests when trying to reconcile brightness with size. Observers measure the object's apparent magnitude, its brightness as seen from Earth. Converting this to absolute magnitude, brightness at a standard distance, requires knowing the distance, which orbital mechanics provides. Converting absolute magnitude to size requires knowing the albedo, which is unknown. The calculation becomes circular. Assume an albedo, get a size. Assume a different albedo, get a different size, without independent measurements. The degeneracy can't be broken. Thermal emission offers a way out. Objects warmed by the sun emit infrared radiation according to their temperature, and that temperature depends on the balance between absorbed sunlight and radiated heat. Measuring the infrared flux allows calculation of temperature, and temperature combined with distance from the sun constrains the albedo size combination. But thermal infrared observations require space-based telescopes or specialized ground-based facilities, and securing time on these instruments for a faint, moving target is challenging. Proposals have been submitted. Observations are pending. For now, the albedo remains uncertain. The darkest solar system objects are typically rich in carbon, either as amorphous carbon or as complex organic compounds. Carbonaceous chondrite meteorites, which fall to Earth from asteroids, contain up to 5% carbon by mass, including organic molecules, graphite, and other carbon phases. When exposed to vacuum and sunlight, these materials darken further as volatile components are lost and radiation cross-links molecules into larger, more stable structures. The result is a surface that absorbs across the entire visible spectrum, reflecting only a few % of incident light. Cometary surfaces darken through a different process. As ices sublimate, they leave behind a lag deposit of dust and refractory organics that can't sublimate at solar system temperatures. This lag deposit accumulates over time, forming a crust that insulates the ice beneath and reduces reflectivity. The crust is porous, filled with voids and irregularities that trap light through multiple scattering, absorbing photons that would otherwise escape. The longer a comet remains active, the thicker and darker its crust becomes, until eventually the surface seals completely and outgassing ceases. The comet dies, leaving a dark, inert nucleus that resembles an asteroid. This object might be such a dead comet, exhausted by millions of years of wandering through regions of space occasionally warmed by distant stars, or it might never have been particularly icy, formed in a warmer region of its birth disk where volatiles were scarce, or its darkness might reflect something else, a composition or surface texture not represented in the solar system's inventory. The albedo alone doesn't distinguish between these possibilities. Surface roughness affects albedo in ways that complicate interpretation. A smooth surface reflects light specularly, like a mirror, with reflection angles determined by geometry. A rough surface scatters light diffusely, sending photons in many directions. At the microscopic level, cometary surfaces are extremely rough, covered with dust grains, ice crystals, and porous aggregates. This roughness enhances absorption because photons bounce between surface features multiple times before escaping, and each bounce offers a chance for absorption. A rough black surface appears even blacker than a smooth black surface when viewed from most angles. The object's surface, whatever its composition, is probably rough at scales ranging from micrometers to meters. Eons of micrometeorite impacts would have pulverized the surface, creating a regolith of fine dust and fragments. Radiation processing would have altered grain structures, perhaps sintering them together in places, creating a heterogeneous texture. Thermal cycling, as the object occasionally passed near stars, would have introduced stresses, cracking some areas and compressing others. The accumulated damage of deep time leaves no surface pristine. Color provides another clue, or another ambiguity. The object's spectrum shows a red slope, meaning it reflects more light at longer wavelengths than at shorter ones. This reddening is common among outer solar system bodies and is generally attributed to organic compounds. But the degree of reddening varies. Some trans-Neptunian objects are extremely red, their spectra rising steeply toward the infrared. This object is mildly red, less so than the reddest solar system bodies, but redder than neutral gray rock. The moderate redness suggests moderate organic content, but quantifying moderate requires detailed spectroscopy that hasn't been obtained. Laboratory spectra of organic tholins, synthesized by irradiating ice mixtures, show red slopes similar to this object's spectrum. The tholins are dark, with albedos typically below 10%, and they're chemically complex, containing hundreds of different organic molecules. If the object's surface is coated with tholins created during its interstellar journey, the darkness and redness both make sense. The lack of spectral features also makes sense because tholins produce broad, overlapping absorption bands rather than sharp diagnostic lines. But tholin composition depends sensitively on the starting ice mixture and the radiation environment. Tholins made from pure methane ice differ from tholins made from methane-nitrogen mixtures or from carbon monoxide water mixtures. The radiation dose matters. The temperature during irradiation matters. The resulting spectra can vary significantly. And not all tholins are dark and red. Some are lighter, some are browner rather than redder. Some show spectral features that this object lacks. Invoking tholins explains some observations, but introduces new uncertainties about which tholins and under what conditions. The reflecting properties might also vary across the surface. Some areas might be darker, some lighter, creating a mottled appearance if the object could be resolved. Cometary nuclei often show regional variations in albedo, with darker areas corresponding to active regions where fresh dust has been deposited and lighter areas where older radiation-processed material dominates. If this object has similarly heterogeneous surface, the measured albedo represents some average over the visible hemisphere, weighted by the viewing geometry and rotation phase. Different observations at different times might yield slightly different albedo estimates if the object rotates and presents different faces. The rotation itself remains poorly constrained. Light curves, plots of brightness versus time, can reveal rotation periods and axis ratios for asteroids and comets, but this object's light curve is too flat or too noisy to extract clear periodicities. Either the object rotates slowly, taking days or weeks per rotation, or it's nearly spherical with little brightness variation as it rotates, or the signal is too faint and the noise too large to detect modulation. Long-term photometric monitoring might eventually reveal rotation, but that requires dedicated telescope time and patient accumulation of data points. Spherical objects are rare among small bodies. Gravity alone can't pull kilometer-sized objects into spheres. The material strength exceeds gravitational compression. Asteroids and cometary nuclei are generally irregular, shaped by collisions and fractures rather than hydrostatic equilibrium. But a tumbling object viewed from certain angles might appear nearly constant in brightness if its shape is irregular but happens to present similar cross-sections to the observer as it rotates. Geometry and luck can mimic sphericity. The absorption of light converts photon energy into heat, warming the surface. For a dark object, almost all absorbed energy must be re-radiated as infrared thermal emission to maintain equilibrium. The temperature depends on the balance between absorbed solar flux and emitted thermal radiation, modified by heat conduction into the interior. At the object's current distance from the Sun, surface temperatures should be around 150 to 200 Kelvin, cold by terrestrial standards, but warm enough to vaporize some ices, if they're present. The thermal infrared emission from such a cold object peaks at wavelengths around 15 to 20 microns, well into the mid-infrared where Earth's atmosphere is mostly opaque. Ground-based observations are difficult. Space-based infrared telescopes are needed. Spitzer, which performs such measurements for Oumuamua and Borisov, is no longer operational. James Webb Space Telescope can observe at these wavelengths, but scheduling time requires proposals submitted months in advance. By the time observations are approved and executed, the object may be significantly closer or farther from the Sun, and the thermal emission will have changed. The albedo problem persists, a fundamental degeneracy between size and reflectivity that can't be resolved without independent measurements. The object is dark, probably very dark, possibly among the darkest things detected in the solar system. But how dark? And why? Remain open questions, waiting for more data, better instruments, or perhaps just patience as the object continues its approach and observers continue accumulating photons. Only took photons crossing space for millions of years to arrive, and most of them gate absorbed, not reflected. Models are built from assumptions, each layer resting on the foundation of previous layers. the entire structure supported by observations that constrain but don't fully determine the parameters. A model of cometary activity begins with thermodynamics. The equations governing heat flow and phase transitions. Solar radiation heats the surface. Heat conducts inward. Ices sublimate when they reach their characteristic temperature. Gas escapes, carrying dust. The equations are well established. Textbook physics, validated across centuries of laboratory experiments and theoretical development. But applying these equations to a specific object requires knowing its composition, its porosity, its thermal conductivity, its ice distribution with depth. These properties are not measured but inferred or assumed. For solar system comets, decades of observation have calibrated the typical values. Most comets are loosely packed mixtures of ice and dust, with porosities around 60%, meaning the volume is 40% solid and 60% void. Most have thermal conductivities low enough that heat penetrates only centimeters per day. Most contain water ice as the dominant volatile, with lesser amounts of carbon dioxide, methane, and other species. These typical values, derived from the population of observed comets, feed into the models as baseline parameters. When modeling an interstellar object, the same equations apply. But the baseline parameters become uncertain. Is the porosity the same? Is the thermal conductivity similar? Is water ice dominant? The solar system sample provides no direct information about objects formed around other stars. Extending the baseline parameters to interstellar visitors is an assumption. Convenient and probably reasonable, but still an assumption. If the assumption is wrong, the model's predictions will be wrong. Not because the physics is wrong, but because the inputs don't match reality. This object's behavior challenges the baseline parameters. If it contained typical cometary material with typical porosity and typical ice content, it should be outgassing by now. The models, given these inputs, predict gas production rates easily detectable with current instruments. The observations show no gas. Therefore, either the inputs are wrong or something about the object is atypical. Perhaps the porosity is lower, the material more compact and dense, conducting heat more efficiently and warming more uniformly, but also allowing heat to escape before volatiles can sublimate. Perhaps the ice content is lower, most of the volume occupied by refractory dust and rock with only minor pockets of ice. Perhaps the ice is deeper, buried beneath meters of crust rather than centimeters. Adjusting the parameters to match observations is standard practice, the way models are refined and improved. But when too many parameters are adjustable, the model becomes flexible enough to fit almost any data, losing predictive power. If every new object requires its own custom set of parameters, the model stops being a tool for understanding and becomes merely a fitting function, a mathematical description without physical insight. The line between refinement and overfitting is subjective and often crossed without realizing. One approach involves running many simulations with different parameter combinations, exploring the range of possible behaviors. Monte Carlo methods randomly sample the parameter space, generating thousands of synthetic objects with varying properties, then comparing the distribution of simulated outcomes to observed behavior. This reveals which parameter combinations are consistent with observations and which are ruled out. For this object, such studies suggest that very low ice content or very deep ice burial is required to match the lack of outgassing. But both scenarios push parameters toward the tails of solar system distributions, into regimes rarely observed locally. The models also incorporate rotation, adding complexity. A rotating object exposes different surface areas to sunlight throughout its rotation period. The subsolar point, the location on the surface where the sun appears directly overhead, migrates, creating a moving hotspot that warms and cools surface material periodically. If rotation is fast compared to thermal conduction timescales, The surface temperature oscillates rapidly, preventing deep heat penetration. If rotation is slow, temperatures equilibrate more fully, and thermal waves penetrate deeper. The rotation period affects the depth of sublimation, the gas production rate, and the spatial distribution of active areas. Without knowing the rotation period, models must explore a range of possibilities. Fast rotation, hours per spin, produces one set of predictions. Slow rotation, days or weeks, produces different predictions. The observations don't yet constrain rotation tightly enough to choose between these scenarios. The light curve is too flat, the brightness variations too small or too noisy. The models run both ways, producing ranges of outcomes that overlap but don't converge. Shape adds another dimension. Elongated objects present different cross-sections to the Sun as they rotate, creating variations in the total absorbed flux. An elongated comet tumbling end over end experiences periodic changes in solar heating more extreme than a spherical comet would. The sublimation responds to these variations, potentially producing outbursts when the long axis points toward the Sun and quiescence when it's edge-on. But modeling this requires knowing the shape, the axis ratios, the orientation of the rotation axis relative to the orbit. The observations provide hints, but not certainty. The equations governing all of this are deterministic. Given exact initial conditions and exact parameters, the model produces exact predictions, but the initial conditions are uncertain, the parameters are uncertain, and the predictions become probability distributions rather than single values. The object's behavior probably falls somewhere within this distribution, but where exactly remains unknown until more observations narrow the uncertainties. Comparison between different modeling groups reveals the subjectivity inherent in the process. Different researchers make different assumptions, use different codes, prioritize different parameters. They all apply the same fundamental physics, but the implementations vary. One group's model predicts weak outgassing below detection thresholds. Another group's model predicts complete inactivity. A third group's model suggests outbursts may occur near perihelion. All three models are consistent with current observations within the uncertainties. They make different predictions for future behavior, predictions that will be tested as the object continues approaching the Sun. The divergence between models highlights how little is truly known. The physics is certain, thermodynamics, heat transfer, sublimation kinetics, but the application depends on parameters that remain unconstrained. Models can predict anything within a broad range, and observations haven't yet narrowed that range enough to distinguish between scenarios. The object will eventually either outgas or not, and whichever outcome occurs will retrospectively validate one set of assumptions and invalidate others. But until that moment, all models remain possibilities, built from local data. The models stretch uncomfortably when applied to interstellar visitors. The solar system provides thousands of data points, but all from one stellar system, one chemical composition, one set of formation conditions. Extrapolating to other systems assumes uniformity that might not exist. Stars vary, protoplanetary disks vary. The objects they produce should vary. The models, trained on local samples, might not capture that variation fully. The predictions for perihelion vary widely. Some models suggest the object will brighten dramatically as approaching heat triggers delayed sublimation. Others predict gradual brightening following geometric expectations with no activity. Still others suggest the object might fragment, thermal stresses exceeding structural strength, breaking the nucleus into pieces that quickly disperse. The observations scheduled for the coming weeks will test these predictions, revealing which models were prescient and which were wrong. But even when one model succeeds and others fail, the success might be partial. The right answer obtained from wrong assumptions, parameters tuned to fit without representing true physical properties. Science advances through such ambiguities, gradually narrowing uncertainties, discarding ideas that fail too often, refining those that succeed more frequently. The process is slow and never complete. The models continue running. Simulations executed on computer clusters, equations integrated forward in time, predicting brightness and gas production and trajectory perturbations. The predictions accumulate in tables and plots, presented in papers and proposals, debated in conferences and email threads, and the object itself continues moving, indifferent to the computational efforts spent trying to understand it, following the laws of physics without consulting the models, being what it is regardless of predictions. Only took decades to build the models, and the first real test is failing. The catalogue of interstellar objects will grow slowly, one entry at a time, each requiring months of observation to confirm its extrasolar origin and characterize its properties. This third candidate, still under observation as it approaches perihelion, will receive a permanent designation once its hyperbolic orbit is confirmed beyond doubt. The designation will encode the year of discovery and a sequence number, bureaucratic and impersonal, offering no hint of the object's origin or composition. It will join 1 I/Oumuamua and 2 I/Borisov in the catalogue. 3 points in a parameter space that remains mostly unexplored. Future surveys will find more. The Vera Rubin Observatory, scheduled to begin operations soon, will scan the entire visible sky every few nights, its enormous mirror and advanced camera capturing faint objects that current surveys miss. Computer algorithms will process the data in real time, identifying moving objects, calculating orbits, flagging those with hyperbolic trajectories. The detection rate should increase dramatically, from 1 every few years to several per year. Perhaps a dozen if the density of interstellar objects is at the high end of predicted values. But detection is only the first step. Characterization requires follow-up observations with larger telescopes, spectroscopy with sensitive instruments, photometric monitoring over weeks or months. Not every detected interstellar object will receive such attention. Telescope time is limited, competition is fierce, and some visitors will pass too quickly or remain too faint for detailed study. The catalogue will contain objects with varying quality of data, some well characterized, others known only from a few astrometric measurements confirming their interstellar trajectory. This object, detected while still inbound and months from perihelion, enjoys better circumstances. Observers have time to plan, to schedule telescopes, to coordinate campaigns across multiple facilities. Spectra will be obtained at various distances from the Sun, tracking changes as the object warms. Photometry will continue through perihelion and beyond, documenting the brightness evolution. If outgassing begins, rapid follow-up will measure gas composition and production rates. If the object remains inactive, that null result is itself valuable, constraining models and narrowing the range of possible compositions. The data will eventually be published, appearing in scientific journals as tables and figures and carefully worded interpretations. Other researchers will analyze the same data differently, propose alternative explanations, test competing hypotheses. Some papers will be cited frequently, becoming reference points for future work. Others will be forgotten, their conclusions overtaken by better observations or shown to be artifacts of incorrect assumptions. The scientific process will grind forward, refining understanding incrementally, never reaching final certainty but approaching closer approximations to truth. Years from now, when the object has faded beyond detection and departed the solar system, astronomers will still debate its nature. Was it a comet with no volatiles, an asteroid from another star's inner system, a fragment of a disrupted planet, A radiation-processed ice ball with insulating crust? The data won't fully resolve these questions, allowing multiple interpretations that fit observations within uncertainties. Future detections of similar objects might clarify whether this one represents a common type or an unusual outlier. Or future detections might all be different, suggesting that interstellar visitors span a wide diversity that defies simple classification. The silence of this passage is assured. The object will not announce its composition or origin. It will not suddenly develop diagnostic spectral features or begin outgassing vigorously in ways that reveal its interior chemistry. It will do what physics dictates given its structure and environment, and observers will record what they can, extracting what information is possible from limited photons and constrained geometries. The encounter is brief. The opportunity is singular. The data collected now is all there will be. Someday, perhaps, humanity will send a spacecraft to intercept an interstellar visitor, to image it close up, to sample its surface, to measure properties directly rather than inferring them from distant observations. Such a mission would require rapid response, identifying the visitor early, launching within weeks, accelerating to intercept velocities. The technology for this exists, barely, in the form of mission concepts studied but not funded. The cost would be high. The scientific return would be immense. A single close flyby of an interstellar object would answer more questions than decades of telescopic observation. But for now, and for the foreseeable future, observation remains remote. Photons travel from object to detector, carrying information encoded in their wavelengths and intensity and polarization. That information is decoded by instruments and algorithms, transformed into numbers and spectra and images, analyzed by researchers who attempt to infer the unseen from the measured. The process is indirect, limited by distance and faintness and the fundamental constraints of remote sensing. It's what astronomy has always been: learning about the universe by studying the light it sends, extrapolating from sparse data to build models of reality. This object will leave, carrying its secrets outward past the planets, past the heliopause, back into the interstellar medium where it spent most of its existence. In a few decades, it will be farther from the Sun than Voyager. The human-made probes launched in the 1970s that crawl outward at speeds measured in kilometers per second. In a few centuries, it will be light years away. In a few million years, it will pass near other stars, other planetary systems, other worlds where perhaps other intelligences watch the sky and wonder about visitors from beyond. The catalog entry will remain: a record of this passage, a footnote in the slow accumulation of knowledge about objects that wander between stars. The entry will include the designation, the orbital elements, the dates of observation, references to published papers. It will note the object's unusual darkness, its lack of detectable outgassing, the ambiguous spectroscopic features. It will mark it as peculiar, awaiting context from future detections that may or may not resemble it. The silence persists not as absence, but as a feature of the encounter. The universe sends messengers, but the messengers do not speak in languages easily understood. They carry information in their motions, their brightness, their spectra, encrypted in physics that must be decoded carefully, interpreted cautiously, always aware that interpretations rest on assumptions that may not hold. The silence is the default state. Speech, clear diagnostic features, unambiguous compositions, behaviors that fit existing models, is the exception. The fortunate case, when observation aligns with prediction, this object defies that fortune. It whispers where clarity was hoped for. It suggests possibilities without confirming any. It moves through the solar system as it moved through interstellar space, silent and dark, reflecting almost nothing, revealing less. The catalog awaits its final entry. the permanent designation that will mark its place in the record. And then the waiting for the next visitor begins. The next whisper from beyond, hoping perhaps for speech, but prepared for silence, only took detection networks, telescopes, instruments, algorithms, and patient observers to find it. And it still refuses to fit the expectations that made the search possible. What Defiance teaches is not immediately obvious, not easily extracted from data tables and spectra and orbital elements. The lesson resides not in what the object reveals, but in what it withholds, not in confirmation of models, but in the discomfort of uncertainty. Defiance in this context is not willful resistance, but simply the property of existing outside prepared categories, of being itself without regard to human frameworks built to contain it. The object defies classification. It's not cleanly a comet, lacking the outgassing and activity that define cometary behavior. It's not cleanly an asteroid, given its interstellar origin and possible volatile content. It occupies the boundary between categories, the liminal space where definitions blur and rigid taxonomies fail. The Defiance teaches that categories are human constructs, useful for organizing knowledge, but not fundamental to nature. And that nature produces objects that ignore the boundaries drawn by limited experience. The object defies prediction. Models built from solar system data predicted brightness, outgassing, spectral features. The object provides brightness, but not at expected levels, provides a spectrum, but not with expected features, might provide outgassing, but not in detectable amounts. The Defiance teaches that extrapolation is risky, that applying local knowledge to foreign contexts requires humility, that the universe is under no obligation to repeat itself in ways convenient for understanding. The object defies expectations about interstellar populations. After Borisov behaved normally, astronomers perhaps relaxed, assuming that most interstellar visitors would be familiar, comet-like, understandable within existing frameworks. This object, like Oumuamua before it, reintroduces strangeness, suggesting that normalcy is not guaranteed, that the sample of 3 objects includes at least 2 outliers, which raises questions about what outlier even means when the sample is so small. The Defiance teaches that early impressions can mislead, that building intuition requires many examples, and that 3 is not many. What Defiance does not teach is the specific answer to specific questions. What is this object made of? Unknown, though constrained to some range of possibilities. Where did it come from? Unknown, untraceable beyond broad directional information. How long has it been traveling? Unknown, though measured in millions of years at minimum. Why is it dark? Several plausible mechanisms, none confirmed. Will it outgas? Maybe, maybe not. Depending on factors that remain uncertain, the Defiance provides questions but withholds answers, which is frustrating but also instructive. Frustration signals the limits of knowledge. Instruction comes from recognizing those limits. The broader lesson concerns diversity. The galaxy contains hundreds of billions of stars, each potentially surrounded by planets and planetesimals, each system formed under slightly different conditions, enriched by different histories of nucleosynthesis, shaped by different dynamical evolutions. The objects ejected from these systems should vary, reflecting the diversity of their origins. Some will resemble solar system bodies, some will not. Expecting uniformity is statistically naive. The galaxy's chemistry varies with location and time. Star-forming regions near the galactic center have different metallicities than regions in the outer disk. Stars formed 10 billion years ago had different elemental abundances than stars formed recently. The objects produced by these varied environments should show corresponding variation. This object, in its Defiance, might be the first clear example of that variation, or it might be an outlier, unusual even among interstellar visitors. Distinguishing between these possibilities requires more data, more objects, more points to define the distribution. The Defiance teaches patience, the necessity of withholding judgment until samples are large enough for statistical confidence. Science proceeds by accumulation, not by revelation. Each object adds information, but conclusions emerge slowly from aggregated data, not instantly from individual cases. The Defiance also teaches about the tools and methods. Spectroscopy is powerful, but not omnipotent. Faint objects with featureless spectra resist characterization. Thermal emission measurements require space-based infrared instruments that are expensive and oversubscribed. Astrometry can detect non-gravitational forces, but not always identify their source. Every method has limits. Sensitivities below which signals vanish into noise. Ambiguities that can't be resolved without additional information. The object's Defiance exposes these limits, showing where current capabilities end and where future improvements are needed. Better instruments will help. Larger telescopes gather more photons, improving signal-to-noise for spectroscopy and photometry. More sensitive infrared detectors measure fainter thermal emission. Advanced coronagraphs block starlight to detect faint comae closer to the nucleus. These improvements are incremental. Engineering challenges gradually overcome through funding and development. Future interstellar visitors will be characterized better than this one. Their spectra clearer, their sizes more certain, their compositions less ambiguous. But even the best instruments can't extract information that isn't there. A truly inert, featureless object will resist characterization regardless of detector quality. The Defiance might eventually resolve. If the object begins outgassing near perihelion, spectroscopy will reveal gas composition, constraining interior chemistry and formation environment if it fragments. The fresh surfaces will provide glimpses of interior structure and strength, if it remains silent. That silence is itself informative, ruling out volatile-rich compositions and supporting models of depleted or deeply buried ices. Each outcome teaches something. Though some lessons are clearer than others, philosophical implications hover at the edges of the discussion, rarely stated explicitly in scientific papers, but present nonetheless. The object is real, physical, governed by deterministic laws, yet it resists full understanding. Does this reflect limitations of human knowledge, or is there something fundamentally unknowable about objects observed only briefly from vast distances? The question is ancient, debated by philosophers for millennia, and a dark interstellar visitor offers no definitive answer, but it illustrates the tension between the existence of objective reality and the partial, uncertain nature of human access to that reality. The teaching continues as long as observations continue. Each new data point refines constraints, narrows possibilities, updates probabilities. The object will teach until it fades beyond detection. And even then, the teaching persists in the form of archived data that future researchers can reanalyze with new techniques or new insights. The Defiance is not permanent, but temporary, lasting only until sufficient information accumulates. Whether that information will accumulate from this object or from future visitors remains to be seen. The galaxy sends teachers, though whether humanity proves a willing student is less certain. The lessons are subtle, encoded in faint spectra and astrometric residuals, requiring patience and care to extract. The Defiance is gentle, not hostile, simply the natural result of observing complex objects with limited tools from great distances. It invites humility, curiosity, and persistence. It rewards those who can tolerate ambiguity while working to reduce it. It punishes hubris, the assumption that local experience translates universally. This object, this third whisper from between the stars, defies the fit precisely because the fit was built from too little data applied too confidently. The models will adjust, the categories will expand, the expectations will recalibrate, and the next visitor will arrive, carrying its own lessons, confirming some new predictions and defying others, perpetuating the cycle of learning that proceeds not in straight lines, but in spirals, returning to old questions with a new context, approaching understanding asymptotically without ever quite arriving. Only took 3 visitors to teach that 3 is not enough. The lesson continues. The object continues, not toward any destination, not with purpose, but in accordance with gravity and momentum, following the trajectory carved through space by forces applied long ago. It moves through the inner solar system now, the sun brighter than it has been for millions of years, warming the dark surface by degrees measured in tens of Kelvin. The warmth changes nothing essential. The surface absorbs, the interior remains cold. The motion persists. Observers watch, but the watching grows quieter. The data points accumulate in files, the spectra stack in archives. The questions, asked and re-asked, begin to repeat without new answers emerging. The object offers what it offers. No more. And the offering is nearly complete. Soon it will pass perihelion, swing around the sun, begin the long climb outward. Soon the brightness will fade, dropping below the thresholds of smaller telescopes, then larger ones, until only the most sensitive instruments can detect it, and then not even those. The silence that surrounded it in interstellar space will return, but now that silence is shared, witnessed, measured. Astronomers have added it to the catalogue, given it numbers and letters, published observations in journals that will be read by few and cited by fewer. The object becomes data, reduced from physical presence to abstraction, a collection of measurements that represent but do not contain the thing itself. It will leave as it arrived, unrevealing. The dark surface will continue reflecting almost nothing. The interior will remain locked. The chemistry that encodes its origin will stay encrypted, untranslated, silent. It crosses through the solar system without speaking, without offering the clear signals that would decode its past. It simply is, and that being is sufficient unto itself, requiring no interpretation, no understanding, no witnessing at all. The universe continues producing such objects, ejecting them from planetary systems, scattering them through the galaxy, sending them on million-year journeys between stars. Most will never be detected. Most will pass through the solar system unobserved, too faint or too fast or too far from Earth's orbit. This one, caught by chance and patience and instruments sensitive enough to register its faint reflected light, represents billions more that drift unseen. The drift continues. The object moves outward now, slowly, imperceptibly, unless measured over days. The sun shrinks behind it, the warmth fades, the surface cools back toward the equilibrium temperature of interstellar space, a few degrees above absolute zero. The thermal whisper of the Big Bang still echoing through empty regions. The object will cool for decades, for centuries, for longer than human civilizations have existed, returning to the temperature it held before this brief encounter with warmth. And eventually, after time spans that erase meaning, it will pass near another star. Perhaps that star has planets. Perhaps one of those planets hosts observers with instruments and curiosity. Perhaps they will detect this visitor, measure its brightness, puzzle over its darkness, write papers about its defiance of their models. Or perhaps not. Perhaps the object will pass unnoticed, as it passed unnoticed through countless stellar systems before this one, drifting in darkness, carrying secrets no one will ever decode. The stillness of deep time settles over it. The patience of geological processes extended to galactic scales. Motion continues, but change slows to rates measured in eons. The object persists, unchanged and unchanging, a fragment of some ancient disk now scattered beyond recovery, beyond identification, beyond meaning except the bare fact of existence. Sleep, wanderer. The journey continues, longer than any story can follow, quieter than any instrument can measure. Sleep in the dark between stars, where no questions reach, where no models apply, where being is enough. The observations end, the telescopes turn to other targets, the data files close, the object fades. Stillness, silence. The gentle, endless drift of things through space, going nowhere, coming from nowhere, simply present in the vast dark, patient and cold and alone.